Hello. This video is part 2 of our atomic structure and periodic trends video. And this one will be focused on periodic trends. If you didn't watch the other one and you're still confused on atomic structure, go back and do that one first because we'll talk about some things that we went over in that video. Okay, yeah, let's get started. For this one, I won't do the actual slideshow because I'm going to click back and forth between this and my browser. Yeah. Anyways, the first trend is one that Miss Melissa did not talk about in the Edpuzzle I had you watch. It's the valence electron trend. Now, if you don't know what that is, a valence electron is an electron that exists on the outermost shell of an atom, okay? I showed you how to draw an atom in the other video, what that looks like, where you can see the valence electrons. And forgot to mention that each group, and that's a vertical row on the periodic table, has the same number of valence electrons, which is just so mind-blowing because when the periodic table got put together, we had no idea what electrons were, what protons were, even what atoms were, and yet it lines itself up that way because the way that an atom will react has to do with the valence electrons that it has. So I'll show you what I mean. In group 1 or 1A here, all of these atoms will have one valence electron, and that's the neutral atom, not the ions that will form. But they will all form a +1 ion, okay? In group 2 here, beryllium on down, all of those atoms will have 2 valence electrons. They'll want to lose both of those to get their full octet and be more stable. They will all want to form a +2 charge. We're going to skip the transition metals because they break the rules because they have that weird d orbital going on. Let's go over to boron though. This is group 3A or group 13. Just depends on the country that you're in. I'm pretty sure that Americans do the 3A and everyone else does group 13. I'm not sure. I might have that backwards. I don't know. But all of the atoms in group 3A have 3 valence electrons. And in group 4, they have 4 valence electrons. Group 5A has 5. Group 6A has 6. Group 7A has 7. And group 8A or 18 have 8. Except for helium. Helium is our oddball. It has a full valence shell at 2 because it only has that 1s orbital that it's working with. So yeah, that's one trend. That's important. That will come up more when we start working on bonding in a couple of weeks. Maybe not even that long. Anyways, moving on. Oops. Okay, so real quick, I want to compare the electron. You know what? I think I'm in the way. I'm going to hide. It was good to see y'all, though. That's better. We're going to compare the electronegativity of this list of atoms here. Just a reminder, electronegativity is the ability of an atom to attract electrons. And I want to order this list from lowest to highest. I wonder how can we make this work without it being too painful. Let's just try this. Let's see how it goes. I've never done this before. We have chlorine here. We have fluorine here. I have potassium. No. Oh, that's so depressing. Okay, whatever. I had potassium. I can't even focus now. Oh my gosh. I'm so sorry. I'm not even going to re-record this because I honestly don't even have time to do that. Okay. Fluorine and chlorine are right here. You had potassium. Who else are we looking at? Magnesium, phosphorus, rubidium. So magnesium, phosphorus, and rubidium. Again, start a GoFundMe so Miss Acuna can get a Surface Pro. Okay, we're going to compare these guys for electronegativity. So remember from the video, if it's closest to fluorine, That's going to be our most electronegative. That was supposed to be a star. Fluorine's the most electronegative, so we know it's going to have the highest. We're just going to put F on the end here. And then anything that's closest to fluorine is going to have more electronegativity going outwards. So our general trend for electronegativity is, it increases going that way, and it increases going this way. Yeah. Or if you want, you can do a giant arrow cross, but I don't suggest you do that. Anyways, with that trend in mind, chlorine will be the next highest. Phosphorus will be the next highest. Then magnesium. Oh my gosh. Then potassium. Then rubidium. And that is all. Now, why is this the trend is the question. So our shell number, and that just means how many shells of electrons we have, that's going to stay the same moving across a period. So moving from left to right. For example, this first one, period 1, let me change the color. Period 1 has 1 shell. Period 2 has 2 shells. Period 3 has 3 shells, and so on, okay? So let's look at period 2 here. If we have 2 shells, but our number of protons is increasing, what happens is the atoms, as you go across, get better and better at pulling in electrons to itself, with an exception being our noble gases. They're happy. They're not going to ask for any more. So yeah. But if we have more shells, we get more of what's called electron shielding. So that pull becomes weaker and weaker as we go down the table. Okay? So yeah, that's why the trend is that way. Did I have more notes? Nuclear charge increases, shell number. Yep. Go me. All right, so that's electronegativity. Ionization energy, just a recap, is the energy required to remove an electron from the atom in its gaseous state. So how much energy does it take to take away an electron from these guys? The trend is the same as electronegativity, so I'm not even going to play with this anymore. It's the same trend. And why? Just think about it. Electronegativity is its ability to attract electrons to itself, fluorine being the strongest. So if fluorine is the strongest, guess what? It's going to take more energy to remove an electron from fluorine than it is from rubidium. So this trend stays the same for ionization energy. Moving on, atomic radius is the size of an atom. So how big or small is it? It's pretty straightforward. This trend is the exact opposite. So let me pull out my eraser here, my handy dandy eraser. This trend also relates to electronegativity. Not directly, but I kind of like to think of it that way. We will see the reverse where atoms actually get smaller going this way. So they get larger going down a group, and they get larger going across the period from right to left this time. So our largest atom is going to be francium over here. Smallest will be helium. And helium, because it only has 1 shell of electrons, so keep that in mind. As we're moving down, we're getting more and more shells of electrons, so they're just going to get bigger. And going across the period, that's where it gets a little bit tricky. For example, for comparing phosphorus and chlorine, that's going to relate back to electronegativity. Since chlorine is stronger at pulling in electrons, it's going to be smaller than phosphorus. I kind of think of it as like, I don't know. Actually, no, I don't know how I think of it. It's just this one's stronger, so it's pulling its electrons closer to itself than phosphorus, which is a bit weaker in electronegativity. It can't hold its electrons as close. It has a larger atomic radius. So this would be the reverse trend, with rubidium being the biggest and fluorine being the smallest. And it looks like accidentally I wrote them Like this F is physically smaller than this rubidium. Anyways, I'm so tired, you guys. That is all. That is all for periodic trends. I just wanted to recap that really quick because I feel like the video I had you watch on Edpuzzle, it was really good. There's a lot of good information, but I just wanted to summarize it really quick. I forgot to write down where you can find practice examples. So let's see. I have the book right in front of me. I'll get back to you on that. But there are practice problems. I just had to find them. I'm going to do that right now. I'll see y'all next time.